Hi there. Um, Welcome to the second part of the Simplex method solution. In the first part, we saw the underlying concepts of the Simplex method, which were geometric, but we also said that in order to implement this in computers, which we usually do, then we had to transform the model into algebraic form. So this is we are going to see how to do that in a minute. So this was the original model, and in this form, we said we were fortunate because it was a standard form maximization problem with all functional constraints less than or equal to, and finally with a negative constraints. Okay, now we are going to introduce what we call slack variables to change basically these inequalities to equalities. And please note that we don't include slack variables in the transformed model in the objective function of the transform model. So the reason is because in the older model we had we had no inequality in the objective function. So we don't change anything here. But here, because we are changing the inequalities to equalities, we introduce slack variables. And in short, slack variables are just idle resources. So if we use some part of this resource and we don't use all of it, then that's why we use it less than or equal to. But now it means when the unused part and the used part you take together, then they have to be equal to 4. Okay, and so on. So next, there are some definitions which just we saw, for example, corner point solution for the geometric description, and the counterpart of this for the augmented is the basic solution, and a basic feasible solution is again another counterpart of CPF or corner point feasible solution. Two more important things: basic variables. These are just slack variables for the initial step. Please note that I say initial step because you could see basic variables in the next steps which are not slack variables. But here, to start with, basic variables in the initial step are just slack variables, and non-basic variables are the variables that are set equal to 0. And here in the initial step, the variables we set to 0 are the decision variables. Okay, so in the first step, basic variables are in short slack variables, and non-basic variables are the decision variables. And in other steps, they might interchange. Okay, so now we have these equations, all equalities, and we also have, please note that we also have the objective function also included here. And this is the first step, initialization. Okay, so when we initialize, we solve this, and because x1 and x2 is equal to 0 in the initial step, then we find the slack variables equal to, for example, x3 equal to 4, x4 equal to 12, and x5 equal to 18. And we move to the optimality test, which says that because these decision variables are 0, then objective function is equal to 0 for the initial basic feasible solution. So for this step, we have this solution. And we move to the next step, which is iteration. And there are basically two steps within the iteration step. And the first is where direction of movement. Are we going to increase x1 or x2? Because both of them are currently 0. So which one are we going to pick first? We look at the coefficients and we choose the one with the highest coefficient. In other words, we choose the one with the highest rate of improvement in the objective function. And in this case, it's x2. So we increase x2 from 0 because this decision variable was 0. And now we increase. As we increase, it changes status from non-basic to basic variable. So now it becomes entering basic variable. Okay, so that's half the iteration. We pick x2, but which variable is going to replace it? That's the next half of the iteration. And another way to say this is how far can we increase x2 before stopping? And this is actually answered by with the help of this minimum ratio test. In other words, we look the equations and we see how x2, the variable we picked to become our entering basic variable, how it affects the other variables. For example, x3, increasing x2 does not affect x3 because x3 does not depend on x2. So there is no upper bound on x2 if we look at x3. But if we look at x4 and x5, because they are dependent on this x2, then we will see that, for example, if we increase x2 to 6, then x4 drops to 0. So x4 drops to 0 when we reach x2 at 6, x2 is equal to 6, and x5 drops to 0 when we reach to x2 is equal to x5 drops to 0 when x2 is equal to 9. So here the limiting variable is the one that drops to 0 first, because if we continue to the next one, then that means this variable can become negative, and if it becomes negative, it violates our restrictions, and because we are going to leave the feasible region. So this variable here is the limiting variable because it drops first to 0. In short, x2 can be increased until one of the basic variables drops to 0. When the first basic variable reaches to 0, as we increase x2, we stop. So in this case, we stop when x4 reaches 0, which means we stop at the point where x2 is equal to 6. Because if we don't stop, we will be violating, as I said, the non-negativity constraint. Okay. We perform elementary algebraic operations to reduce the original system of equations to perform from Gaussian elimination, where each basic variable has been eliminated from all but one equation, which means its equation. So, and has a coefficient of 1 in that equation. So, for example, because x1 is equal to 0, x3 can be directly said to be equal to 4. But we cannot do the same for x2 because x2 is here and here and here. And to have just one equation where x2 is equal to something, then we do these algebraic operations. For example, we divide this equation by 2, which gives us x2 plus half x4 is equal to 6. This one, if we divide this by 2, then we get this one. And then 5 times this equation, we add 5 times the new equation to equation 0, which is the objective function equation. And then subtract 2 times this new equation from the third equation, this one. In this way, we will have the x2 appearing only in this equation, and it will vanish from here and here. Then we can directly say x2 is equal to 6 because x4 is equal to 0. Okay, and then we go to the second optimality test. When x1 is equal to 0 and x2 is equal to 6, then objective function is equal to 30. Again, we will see if we can find a better solution. And because now x1 has a positive coefficient, increasing x1 would lead to an adjacent BF solution that is better than the current BF solution. So the current solution is not optimal. So we continue. And when we, after the next iteration, doing the same things we did before, then we arrive this solution. And it means now there is, because both the decision variables have vanished from here, and we have x4 equal to 0, x5 equal to 0, then we have objective function which equal to 36. So in short, we start at the origin, and then the entering basic variable depends on the rate of improvement in Z. The higher, then we choose the one that with the highest rate of improvement. The leaving basic variable depends on the minimum ratio test. After each iteration, algebraic operation is performed to get the proper form from Gaussian elimination. And lastly, but not least, we repeat the iteration until no better solution can be found, in which case we declare we have reached an optimal solution. I hope this helped and you found it useful. Thank you very much.